you very much. It's a pleasure to be here again in this seminar. And I'd like to tell you about a sort of topic that I got involved in the past 2 or 3 years that has sort of changed a little bit the way I look at some of these inverse problems in dimension 2. So here's a little bit about the plan of the lecture. So along the way, I think I'm going to remind you, or if this is new for you, about some kind of landmark actual results in geometric inverse problems in 2D. I will tell you a little bit about how these ideas have evolved and how we can actually see them today through the lens of a suitable complex surface that in due time I'm going to attach to our objects of interest. Towards the end of the lecture, I'll discuss a little bit about some current developments and some sort of open questions. And I guess another point of the talk is to advertise the book. So I hope you won't mind if I tell you a little bit about the book that just came out. So this is a book with Mikko and Gunther, where you can actually learn quite a little bit about the topics that I will explain here. And I'm just to be clear, I'm not really asking you to go and buy the book. The book is freely available on our web pages. Okay, so there's some background noise having to do with the windows in my office that they open and shut kind of automatically. Okay. Right, so let me tell you first a little bit about the background. It's the usual one for inverse problems in a geometric context. So I have a compact Riemannian manifold with boundary, and most of the action actually takes place in the unit tangent bundle. So I quickly remind you, this is just points and vectors, where the vectors have norm 1, and I measure the norm of the vector with respect to the Riemannian metric. So that's a larger manifold that has dimension. So if M has dimension n, you are adding the sort of dimension of the fibers, so you end up having a manifold of dimension 2m minus 1. And if M has boundary, the unit tangent bundle also has a boundary that you can actually sort of picture in the picture here, where you have, you're sitting at the point at the boundary, and you have vectors pointing in and vectors pointing out. So you have the influx and outflux boundary, and I want to give names to those. So I want to call partial plus of SM the outflux boundary. So if nu is the inner normal, I just want vectors pointing inside, so they have inner product with nu greater than or equal to 0. And if you're pointing outside, you have inner product with nu less than or equal to 0. And to make my life easier, I'm going to assume that the boundary is strictly convex, which this just means positive definite second fundamental form. For some of the things, this is not really needed, but it makes your life quite a little bit easier. Okay, so that's essentially the picture that I want you to have in mind. And I'm going to assume something about the geodesics that on my manifold. So I'm going to say that my manifold is non-trapping if every time that I begin at a point x on the manifold and a tangent vector, and I follow the geodesic, I exit in finite time, a finite time that I call tau of xv. Now, it's a classical piece of geometry that if you have a non-trapping manifold with a strictly convex boundary, it has to be contractible. So you might as well think of these manifolds as just balls from a topological point of view. And you can trace this back to some classical result of Serre in the 1950s by using Moore's theory. And most of the time, I will also assume that it is simple, which means that on top of being non-trapping, I also want the manifold not to have conjugate points. The no conjugate point condition means that you don't have caustics, or if you like, that if you go to the universal cover between 2 points, you have a unique geodesic, which at the end of the day, if it is non-trapping and you have strictly convex boundary, the universal cover has to be the manifold itself because it is contracted. Okay, so those are simple manifolds. And if the geometric background is something that you're not comfortable with, here is a sort of very simple collection of sort of examples. The simple condition is a good condition because it's C2 open in the metric. So namely, if you have an example and you make a C2 perturbation, it remains simple. So you can just begin with your favorite strictly convex domain in Rn, and then you make sort of little bumps on your metric, and that will also remain simple. Okay, so that's the sort of main class of manifolds that people have been looking at for quite a long time. And the most classical object here is the X-ray, in which you essentially integrate functions along all possible geodesics connecting boundary points. So you write this as the X-ray transform, which in principle you can define for any C-infinity function on the unit tangent bundle. So you have such a function, and all that you do is if you begin with a point on the boundary and a tangent vector pointing inside, then you follow the unique geodesic along given by xv, and you integrate that function, and then the outcome of this is now a function on the influx boundary, and this is called the X-ray transform. So phi t here is the geodesic flow, which essentially just packs the position and velocities of the geodesics. And usually you're not interested in the X-ray acting in all possible functions of the unit tangent bundle, but you want to take suitable subspaces or functions in the unit tangent bundle, and the most popular are basically if you take functions on M and you take pullbacks to the unit tangent bundle, so that will be functions that only depend on the position. Or you take a one form and you think of that one form as a function in the unit tangent bundle, or a symmetric two tensor in which you can think of it also as a function in the unit tangent bundle just by simply saying that if I have a unit tangent vector, I input in my symmetric two tensor VV, basically. And this gives rise to I0, I1, and I2, and these are the most popular X-ray transforms that sort of pop up. Okay, so this is the usual classical picture. So I exit in finite time tau. The geodesic flow is just essentially gamma t, gamma dot t, and gamma is the unique geodesic with these initial conditions xv in the influx boundary, which is point on the boundary of M, and then vector pointing inside into your manifold. Great. Now, the following fundamental result, which I guess many of you have seen, underpins everything in this sort of business. And this is essentially the fact that I0 is an injective transform if you assume that MG is a simple manifold. So if I0 of F is equal to 0, then F is 0. And for the case of one forms, there is a natural kernel, which is essentially when the one form is actually exact and the actual potential P vanishes on the boundary, then the fundamental theorem of calculus will tell you that these elements are always in the kernel. But then what you can actually prove is that if the X-ray of a one form is equal to 0, the form has to be exact with a function that vanishes on the boundary. So these are classical results from the late 70s, and they essentially kind of underpin everything that follows. So these results these days can be proved quite nicely in a sort of elegant form using what is known as Pestov identities. That's something that you can definitely find in the book with Mikko and Gunther. Great. Now, once you have the X-ray, I quickly remind you about the adjoint, which is the back projection operator. And this is the adjoint with respect to a suitable inner product. The inner product that you actually put on the influx boundary, you have a kind of canonical inner product in which you would just simply do the sort of product measure. But you have a kind of natural measure on the boundary of the manifold, which is inherited from the sort of Riemannian metric, and you will do that cross the volume that comes from the spheres at the point. But that's not usually the measure that you want in this sort of business. You want to weight that measure by a function mu, which is essentially the inner product of nu times v. There are many reasons for the reason why you want to consider that measure, that weighted measure with mu. having to do with symplectic reasons, having to do with the Santalot formula, which is a classical integral formula that relates integrals of functions on the unit tangent bundle with integrals on the influx boundary. I don't want to get into that, but that's a sort of pretty canonical measure. And as I said, it's not the only adjoint you can take, but this is the one we want to look at. And that adjoint I0 star has a very nice way of expressing it if you were to consider things in this infinity context. So obviously, I mean, this is a boundary operator, so it does extend the adjoint. I mean, this does extend as a function in L2, so you have a well-defined adjoint. But on C-infinity objects, there is a very nice way of expressing it. So let me quickly remind you about this, which I will tell you in a minute. And for that, I need to sort of introduce one additional key player in this thing, which is the scattering relation. The scattering relation of the metric is just simply, you have point and vectors pointing inside, and you just simply look at the exit point and the exit vector. So that gives you a map from the boundary of the unit tangent bundle to itself that essentially maps outflux to influx and influx to outflux if you just simply run things backwards. Now, using the scattering relation, you can look at this very special set of functions on the influx boundary, which are essentially the functions that are the restrictions of functions on the whole boundary of the unit tangent bundle, which are invariant under the scattering relation. Yeah, so basically, I take a function which is a C-infinity function in the unit tangent, in the boundary of the unit tangent bundle, with a property that it is invariant under alpha. So that means that you look at the function h here, and you look at the function at a point alpha of xb, and it has the same value, and then you take a restriction of that function to the partial plus. And I sort of denote this subset of the set of all possible C-infinity functions on the influx boundary by C-infinity alpha. So this is a space that was introduced by Pestov and Ullmann in 2005, roughly, and you will see why in a minute, because it can be related essentially with first integrals of the geodesic flow, which they can be constructed in the following very simple way. If you take a function on the influx boundary, you can make it very easily into a first integral, namely a function in the whole unit tangent bundle, which is invariant, which is constant along the orbits of the geodesic flow. And you just do the obvious thing. If you want to define what this function is on a point xv in the unit tangent bundle, you just simply run that point xv backwards. Yeah, that's the meaning of that, until you hit the outflux boundary, and you let that function that you want to define to be the function that you have on the influx boundary. So going back to this picture, if you want to define what the function is at a point x and v there, you just run it back, and then you say, well, that's going to be my function w on that influx point and vector. And the nice thing that happens is that you can identify now these two things. So C-infinity first integrals are essentially given by this process, as long as you begin with a function in the influx boundary that comes from one of those nice infinity functions on the whole unit boundary of the unit tangent bundle, which are invariant under the scattering relation. So this is a very nice way to connect or to actually characterize C-infinity first integrals of the geodesic flow just by going to the boundary and seeing what is happening on the boundary. This is essentially a kind of result in differential topology, if you like, using basically, the theory of faults on the boundary. That's, again, another result whose proof you can find in the book. And for this, you don't need the simple property. It's just enough to have a non-trapping manifold. So once you have identified that space, then the adjoint has this sort of very nice sort of expression. Now, it goes from the space C-infinity alpha into C-infinity functions in M, in which you just essentially do sort of integration on all the fibers of this first integral. So basically, this is sort of telling you that if you want to compute this back projection operator, you take a function on this infinity alpha, a function on the influx boundary, you make it into a first integral of the geodesic flow that by this theorem gives you a C-infinity first integral, and then you just average on each fiber, and the outcome should be also a C-infinity function on M. So that gives you this map between C-infinity objects, basically by making the function a first integral and then doing a push forward. Great. And somehow the key result that kind of underpins a lot of these geometric inverse problems in 2D is this surjectivity result of Pessoa and Ullmann from 2005 that tells you that the I0 star is actually always onto. So given a infinity function on M, that function will always be coming from this sort of process. Basically, I want to go back. Will always be coming from this sort of process. You can always find a smooth first integral such that when you push it forward to M, it hits the function f that you have given. And the basic idea for this theorem is quite simple, if you like. It goes back to this sort of Keyes sort of observation that the normal operator I0 star I0 is an elliptic IDO of order -1 in a slightly larger manifold that actually surrounds your manifold M. So this is where somehow the non-conjugate point condition that people call also the Volcker condition in this case, so this is all in some sense fairly classical, comes into play. And using the sort of ellipticity of this operator, you can show that this map has close range essentially. And then from the injectivity result of the X-ray, which I told you a little bit earlier, is the fundamental thing that underpins everything, you can prove that this is actually surjective. Okay, great. Now, to get to the point that I'm really interested in, I need to look at the geodesic vector field. Now, I want to think about it as a usual first order kind of differential operator acting on functions on the unit tangent bundle. So let me just remind you what the X is. So I call it X, and it's a first order differential operator mapping infinity functions to infinity functions, where you just compose. If you have a function, you actually compose it along the orbit of the geodesic flow, and you differentiate at t equal to 0. And now there is this very simple exercise that you can rephrase the surjectivity of I0 star in terms of first integrals. You're kind of saying, well, the surjectivity of I0 star is a solvability result in some sense. So it sort of says that if you give me a C-infinity function on M, I can find a smooth first integral. So we are solving the sort of basic transport equation, xw equal to 0 in the unit tangent bundle, and you solve it in a C-infinity way with the property that the push forward, namely sort of integration along the fibers, gives you the function f that you gave me at the very beginning. So that's just a rephrasing of this basic result of Pessoa and Ullmann. Great. So this is all very general and works in any dimensions up to dimension d. And I'm sure for many of you, this was just a basic review of things that have been known for quite some time. Now, let me specialize from now on to dimension 2. So what is really special in dimension 2? Well, what is really special is in that in dimension 2, one way in which to say that things are really special is that I can do some very nice Fourier analysis on the fibers. So basically, if you think about dimension 2, the unit tangent bundle is a circle bundle of the surface. So at each point, I have a circle, and I'm working for a surface that it is orientable, and that's the only case that I'm going to be looking at. So that means that in my fibers, I have an action of the circle, and with respect to this circle action, I can do Fourier analysis. So that means that I can decompose L2 functions in SM into Fourier modes, vertical Fourier modes. So just simply think that, for each point x on M, you freeze the x and you do, Fourier expansion just in the vertical variable. And so there is this sort of vertical vector field that I call V, and the eigenspaces of this decomposition, I denote them by HK, and the C-infinity ones. So if I take an intersection of C-infinity functions with HK, I call these things objects omega K. So a smooth function in C-infinity M will have a Fourier expansion in Fourier modes where each one of these UK is now a function in omega K. And the nice thing about dimension 2, I mean, you can do this in any dimensions just by looking at the vertical Laplacian. But what happens in dimension 2 is that, in the Fourier expansion, you go both ways. You have, negative Fourier modes and positive Fourier modes because, So in particular, it makes perfect sense now to talk about fiber-wise holomorphic functions. So I would say that a function in C-infinity of Sm is a fiber-wise holomorphic function if all the negative Fourier modes in this Fourier expansion are all 0. Yeah, so this is a sum in Z, which simply, definitely corresponds to the notion that, if it's just a function on the circle and you have all the Fourier modes negative, this function is the boundary value of a holomorphic function on the disk. And there's a converse. If you have a holomorphic function on the disk that has a nice infinite extension to the boundary, when you do the Fourier expansion, you will only have non-negative Fourier modes for your function. So hence the name. So you can do this Fourier analysis, and with respect to this Fourier analysis, the geodesic vector field has a fantastic property that it decomposes essentially into two Cauchy-Riemann type operators called eta plus and eta minus that were introduced by Guillemin and Cashton back in 1980s that have the property that raise a lower degree. So if you have something in omega m, the eta plus will raise index by 1, map it to omega m minus 1, and the eta minus will lower index by 1 and map it into omega m minus 1. So you have this kind of very nice way of looking at the geodesic vector field as the sum of two Cauchy-Riemann type sort of operators. So just as a quick example, in the flat case, is a very easy sort of exercise. I mean, in that case, the geodesic vector field is a sort of classical, V dot product grad X that usually appears in the transport equation, and writing, V dot product grad X as a sum of e to the I theta, the D and the D bar operators is a very simple exercise. So you can see now what I meant here, but this is totally general, works for any surface. So now you have the situation that your surface has a metric, and once your surface has a metric, it becomes naturally a Riemann surface, because if you have an orientation, you have a natural way of multiplying by I, where you just simply take a vector and you rotate it by 90 degrees, sort of according to the orientation of the surface. And by 90 degrees, you use the metric to say when two vectors make a right angle, and that gives M naturally the structure of our Riemann surface. And then is, again, an easy exercise to check that a function is holomorphic as a function in the Riemann surface, if and only if, when you think of this function as a sort of the pullback to Sm, is being killed by eta minus. Yeah, which again, this would be kind of immediate to check. I mean, it's very easy to check in general, but would be obvious to check if you just look at this formula here. Right, so, and this is because of what is coming up in a minute, I have somehow quite naturally two ways of thinking about holomorphic objects. I have the vertical Fourier decomposition and the notion of fiber-wise holomorphic. But then I also have, the underlying structure of Riemann surface, that it is in some sense encoded in these operators eta minus. And somehow what is going to come up in a few minutes is a way to reconcile these things. But just before I do that, let me just go back now a little bit in 2D and see the special feature that pops up in 2D for the Pester-Woolman result. So the Pester-Woolman result told us that if you give me a sinfinity function in M, I can find a sinfinity integral, for x, such that the push forward is exactly the given function f. But now if you're in dimension 2, you can begin with a holomorphic function on M, for instance, and then ask yourself, well, what kind of property do you get for the first integral? Okay, is this first integral going to be special in any way? Well, it's not at all difficult to see that from the Pester-Woolman result, you get that actually you're allowed to choose your first integral to be actually fiber-wise holomorphic. And this is simply that, the Pester-Woolman result will give you just a first integral, and all that you have to do is essentially pick, let's say, the even positive Fourier modes of that, and you can just check that this would be a first integral simply because if you began with a zero Fourier mode being killed by eta minus, then you can just check from the properties, the mapping properties of x that I told you before, that the x of u, if you just take the positive Fourier modes, will just be equal to 0. So if you begin now, so this you get a little bit of an upgrade. If you begin now with a holomorphic function on M, you can get now a first integral that in addition has the property that is fiber-wise holomorphic in the vertical Fourier decomposition. So that's super nice for many reasons, but it's special to dimension 2. And this is the way we thought about this thing for quite a while, and we were all pretty happy thinking about this in this way. And it is possible to sort of continue life thinking about this more or less forever. But somehow, you feel that there might be a way of putting these two things on kind of equal footing, fiber-wise holomorphicity and the holomorphicity coming from the Riemann surface. And this is exactly where this transport twistor object comes into the scene. Okay, so what is this object? So before I tell you what it is, and I get maybe just a little bit technical about the way you actually define it, let me just tell you that a few general features about it. So it's going to do exactly what I told you. It's going to put on equal footing the fiber-wise direction and the horizontal direction. But it does it in a non-trivial way, as you will see in a minute, because we want to preserve the property that the geodesic vector field acts on this sort of function. So we want also first integrals. So hence the name transport, because this is really connected as you go to the boundary, to the transport property, or to the transport equation. Okay, now, what is this object? Well, this object ends up being, from a topological point of view, completely trivial. And in some sense, it's what you would expect, right? Because, we were looking at functions that were fiber-wise holomorphic, and I told you that, those are essentially functions that do have a holomorphic extension to the disk. So it makes complete perfect sense just to kind of fill in the vertical fibers of the unit tangent bundle with disks. And there's no easy way to do that than to consider just the disk bundle. So the unit disk bundle is essentially you look at vectors with norm less than or equal to 1 rather than equal to 1. No problem there. That's a real 4-dimensional manifold, and the unit tangent bundle sits on the boundary of this space set. Naturally. I mean, if your manifold M has boundary, the manifold set ends up being a manifold with corners, but if your surface were to be closed, this set is just a regular manifold with boundary, and the boundary is just a plain all unit tangent bundle. Now, it turns out that the interior of this transport twistor space is very naturally a complex surface. Complex dimension 2, and it has a very nice sort of additional feature that the zero section embedding, because the zero section is there, because I told you all vectors with norm less than or equal to 1, so the vector v equals 0 is there. gives you a copy of M, and that embedding is holomorphic. Yeah, so M is a Riemann surface, and now you get this sort of natural embedding of M into Z, and that is a holomorphic embedding. That's nice. Now, it is a complex surface just in the interior, but the nice thing is that as you go to the boundary, the complex structure degenerates, and it picks up exactly X. Yeah, you will see that in a minute, how it happens in action. So this is why it's really tailored to the geodesic vector field X. Now, in some form, or maybe in a different kind of dressing, or I mean, this object has been around for quite some time, but maybe not in the language that I am actually describing it. So you can trace some of these origins back to Hitchin and Lebrun in the 80s, and then people have actually considered this, many other authors. But after you look at these things with some care, you see that the object that you're interested in, the set that I'm actually interested in, is not the one that most people use, but it's actually a 2-to-1 branch cover over the usual one. And this 2-to branch cover is really kind of pretty crucial for us, because if we were to work with the other one, with the classical one, essentially we will be missing out on half of the invariant objects, to more or less describe this briefly. And this is, you don't want to do that really for these geometric inverse problems. You wouldn't be able to do the things that we want to do. So it is important to work with this sort of 2-to-1 branch cover. Okay, so this is roughly, first description. So on a little bit more technical level, how do you sort of introduce, how do you actually see this as a complex surface? Well, this is one way to think about it. So you add a sort of additional variable, let's say omega, and you first work on the unit tangent bundle cross D. So you go to a 5 manifold, basically, and now there's going to be a map that drops down dimension by 1. But once you do that, you look at this sort of two innocent looking complex vector fields, if you like. So this is the usual one, d omega bar, or the d bar in the omega variable. And then you do this thing. So remember, the eta minus is essentially carrying the sort of information of holomorphic objects in M. And then you twist it a little bit with this omega square eta plus. And that's what you do. So all the magic in some sense is in this little twist. If you didn't put that twist, you will get something that is a complex surface, but it would be like kind of the obvious thing, like sort of taking some kind of product, fiber base. And that will not really catch the vector field X. So it will not degenerate in the boundary in the way that you wanted if you want to discuss transport problems. So you look at these two things, and essentially what happens is that there is a natural map now from this product Sm cross T into Z, in which what you do is, well, you do nothing in the X, but if you have V and omega, so omega is just a complex number, but you have the structure of a Riemann surface on M, so I can actually multiply that complex number times V, basically. And that's a map that will essentially take me Sm cross T into Z, and will drop dimension by 1. Now, it turns out that you can push forward this two-plane bundle, and this two-plane bundle is actually an involutive two-plane bundle. Maybe if you take the Lie brackets of these two things, you end up being inside things. And that's the kind of integrability condition for having exactly a complex surface. And this comes out of, kind of cheaply in a way, just from the structure equations of your surface, basically. If you set it up using the eta plus and eta minus, which is, this eta plus and eta minus from Guillemin and Castanen, really good ways to think about this. And, once you push it forward to Z, this essentially gives you the 0-1 tangent bundle. And now you think of a function being a holomorphic function when you pull it back to Sm cross T, is being killed by these two vector fields. And that's essentially this transport twistor space. The nice thing about this is that once you go to the boundary, this actually, you pick up sort of exactly X, because it is as if, you are allowed essentially to set here omega equal to 1. That will give you the X, because, you go down to the quotient and then you have a little bit of an ambiguity acting on the fiber, but that will give you essentially X. And, once you go away and do your homework, this is what this buys you. That now you have a natural one-to-one correspondence between fiber-wise holomorphic first integrals, which are just two objects on the unit tangent bundle, and holomorphic functions on Z. Yeah. So now you were able to capture the two things, being a first integral, being fiber-wise holomorphic, into now an honest holomorphic function on Z. Now, the case that I'm looking at here, because in the last few minutes I will talk about distributions, I'm looking at C-infinity functions on Z that actually becomes holomorphic in the interior of Z, because the notion of holomorphicity makes sense only in the actual in the interior of Z, but this is a perfectly fine one-to-one correspondence. And once you see this, you cannot look at this problem in any other way. You say, all these things that we've been dealing with, these were just honest holomorphic functions on Z that they were actually extending as nice infinity functions on SM, picking up exactly first integrals. So this is great. So you're kind of very happy. And then you start looking at, what this means really. And it's a completely natural thing to think about now the algebra of holomorphic functions. So let's call that AZ. But you also have the algebra of holomorphic functions in M. So let's call that AM. And now you have now a twistor version of the surjectivity result of Pesto-Van-Ullmann, the fundamental result in 2D, which says that if you have a simple surface, then the map that takes a holomorphic function on the transport twistor space and restricts to the zero section is surjective. Or if you like, if you give yourself a holomorphic function on the zero section, that extends to a holomorphic function in the larger ambient twistor space. So this is a little bit like this sort of Catan kind of extension property that the Stein surfaces has. And this is very, very satisfying way of reinterpreting the surjectivity result of Pesto-Ullmann. So this is the first example in which we know we had a slightly different point of view of this key result. And then you go a little bit further and you say, well, the king of all landmark results in 2D is boundary rigidity by Pesto-Ullmann, okay? And within boundary rigidity, the fundamental result is this slightly counterintuitive, remarkable result that tells you that you can go from classical to quantum, and tells you that if you have two simple metrics on the surface, let's say you have already put yourself in the right kind of position by sort of arranging the metrics G1 and G2 to be the same on the boundary, then the key result, the fundamental result, is that if the two scattering relations are the same for the two metrics, the Dirichlet-de Neumann maps are the same. And this is the way they solve boundary rigidity, because once you get that the two Dirichlet-de Neumann maps are the same, you know that you can determine the metrics up to a conformal map, which is the identity on the boundary, and then you're essentially home, going back to Moog-Hometop. So this was the key thing. And there's something a little bit counterintuitive here, as I was saying before, going from the sort of classical object, which is saying that the two scattering relations are the same, to this sort of quantum object saying that the two Dirichlet-de-Neumann maps are the same. Right. So can we actually look at this Pesto-Ullmann result from the optics of twistor space? And the answer is yes. So one way to do this is to say, well, let's look at functions on the boundary of the unit tangent bundle, which are fiber-wise holomorphic and are invariant under the scattering relation. So in some sense, the main insight of the Pesto-Ullmann result is this surjectivity result, that if you have a simple surface and you take a holomorphic function in twistor space and you restrict it to the boundary, that's in fact an isomorphism. So basically at the boundary, you capture all the holomorphic functions in twistor space. Okay, so where does that come from? Well, I'm going to tell you what the inverse map is, right? So Clearly, you can always take the restriction map, and it's going to be an element in H, because things will be fiber-wise holomorphic. But how do we go back? How can we produce from an element in H a holomorphic function in twistor space? Well, you do the following. So I have an element in H, so this is a function in the influx function on the boundary of the unit tangent bundle, and I consider the first integral that it determines. It determines a C-infinity first integral, but then you ask yourself the question, is it fiber-wise holomorphic? And indeed it is, but why? Well, because if you just simply take its negative Fourier content and you just apply the x, you will get something that lives in the space omega minus 1 plus omega minus 0, just purely out of the mapping properties of the eta plus and eta minus. And since you began at the boundary with something fiber-wise holomorphic, it means that once you go to the boundary, this negative part on the boundary is actually equal to 0. But that's exactly the transport problem that you get when you're trying to show injectivity of I0 and I1. So injectivity of I0 and I1, again, going back to Mukhometov and so on in the 70s, will now tell you, yes, you're fine, Gabriel, this function is going to be fiber-wise holomorphic. And all of a sudden, just from the surjectivity, from the injectivity of I0 and I1, you get an isomorphism. Once you get an isomorphism, the proof of Pestov-Ullmann writes itself from a commutative from a diagram. You kind of arrange things in the following way. You say, well, if my scattering relations are the same, the space H that I told you before, let me go back a couple of slides. The space H, you see, it's defined just purely in terms of alpha. So if alpha 1 equals alpha 2, the H is the same for both metrics. There's zero mystery here. So if the H is the same for both metrics, and I have sort of identified H with the twistor of G1 and the twistor of G2, these two spaces are essentially the same. There is a map between the two. And now you can put all this information in a diagram, and you have an arrow going down by the restriction to the zero section, that the surjectivity result of Pestov-Ullmann tells you that is onto, so you can extend. And then you have a map going across that is an isomorphism. And if you just look at what happens at the boundary, you see that everything behaves in the way you want. And then you have a way of saying, well, if I begin with a holomorphic function with respect to G1, yeah, I can go up to twistor, move it forward, go it down, and I will get a holomorphic function with respect to the metric G2. And if you look at what happens at the boundary, these holomorphic functions will have the same boundary values. So all of a sudden, you're saying that for the two structures of Riemann surfaces, the boundary values of holomorphic functions are the same. And now it's an exercise in undergraduate complex analysis to prove that this is the same thing as saying that you have the same Dirichlet to Neumann map. So you have proved that if the scattering relation are the same, you have the same Dirichlet to Neumann map. So that's a way of looking at Pestov-Ullmann from the point of view of twistor space. In the book, we do something very similar, but when we sort of finished writing the book, we didn't have the sort of twistor point of view. But now there is this sort of way of looking at it, and all of a sudden the proof by Pestov and Ullmann, it is a very geometric proof, but it's a complex geometric proof at the heart, with this sort of classy little touch of micro-local analysis coming from the psi-DO property of the normal operator to tell you that these two maps going down are actually surjective. So this is this is the way you think about boundary rigidity. So from my point of view at least, very satisfying. So let's keep moving on a little bit. So in the last few minutes, let me see that somehow kind of you can look at this thing, almost everything that has been done from this point of view. So let's go back to another landmark result by Mikko and Gunther from 2011, that they show that you have always fiber-wise holomorphic integrating factors, essentially. So this is the statement that if you have a infinity function on M, you can solve the transport problem, xw equals -phi with a fiber-wise holomorphic function. So this was, okay, well, I mean, you can rephrase this by taking an exponential, which if you take if you have a fiber-wise holomorphic function and you take an exponential, it remains fiber-wise holomorphic. But you can write this in the following of this sort of transport equation with an attenuation phi. This is another way of showing this. And Mikko and Gunther used this to prove that the attenuated X-ray transform on a simple surface was injective. Very nice result by essentially using this fiber-wise holomorphicity property and essentially moving it to the regular X-ray by getting rid of this phi via this fiber-wise holomorphic integrating factors. So these were great. And the same result, actually, I mean, they did it for a function phi, but, you know, you can, all that you need here to kind of preserve the natural mapping properties is to know that your function phi has negative Fourier modes from degree -2 and down. And here is now the way one can actually see this. So result of Mikko and Gunther is to say, well, really what you're actually proving after you do, again, your homework, is just simply that Z does not have non-trivial holomorphic line bundles. So all of a sudden you have this natural geometric way of kind of interpreting this sort of existence of holomorphic integrating factors in this form. So this begs the question, well, what about higher ranks holomorphic vector bundles? You know, you have a complex surface, your holomorphic line bundles are trivial. You know, what about, you know, an arbitrary holomorphic vector bundle? And then the question is, of course, well, let me just tell you a little bit about this. So if you want to go to higher rank holomorphic vector bundles, then rather than taking, you know, things in GLN G1C, you look at just the general linear group, and really what you want is the correct sort of way to think about this. What would be a holomorphic integrating factor is to have a function in SM which is fiber-wise holomorphic and whose inverse is also fiber-wise holomorphic. This gives a group. Oops. And a function f in this group is called a holomorphic integrating factor for an attenuation A if you solve this equation, this transport equation now in matrices. X plus A applied to f equal to 0, where the f is now, the key thing is that this is an invertible matrix. And once again, you know, the actual existent result, you don't, the right space to look at is this space Mo, where you have Fourier modes being 0 from degree -2 down. This is again because of the mapping properties. If you apply X to something fiber-wise holomorphic, it will only pick up degree -1 and nothing below that. So this arises naturally. And something that we proved, well, a couple of years ago, essentially with Jan Bohr, is that on a simple surface, any element in Mo has holomorphic integrating factors, and you can phrase this exactly by saying that the transport twistor space does not have non-trivial holomorphic vector bundles. And, you know, the main reason for looking at this kind of thing at the time for us was to actually tell what the range of the non-abelian X-ray transform was, and we were able to do that, and we sort of provided a nonlinear analog of the classical range characterization that was given by Pester-Ullmann for I0 for the case of simple surfaces. But once again, in the language of the transport twistor space, you just don't have non-trivial holomorphic vector bundles. Okay, so I have a couple of minutes left, so I think I will finish with 2 slides with some recent developments about what is going on for closed surfaces, which is quite interesting too, particularly if you're interested in questions in dynamical systems. So once you go to closed surfaces, you know, you cannot expect the geodesic flow to have a lot of infinity integrals, right? I mean, in some sense, kind of the opposite. So if you have, let's say, you know, a surface of negative curvature, the geodesic flow, because of ergodicity, is never going to have not even an L2 invariant function. So we are not going to be able to get this sort of kind of rosy picture that we had before for simple surfaces. but it may still have lots of invariant distributions. Yeah, and this may play kind of fundamental role. And in fact, and this was a kind of very pleasant surprise, there is this completely general result. So in the same way as we had a one-to-one correspondence between C-infinity first integrals, which are fiberwise holomorphic, and holomorphic functions in twistor space, what we do have now is a one-to-one correspondence between fiberwise holomorphic distributions, yeah, and holomorphic functions, honest holomorphic functions in twistor space that have a suitable polynomial blow-up as you approach the boundary. And the polynomial blow-up is very easy to actually describe. You just simply say, well, I want my functions f to satisfy this sort of property. As you are in the sort of interior of twistor space, you can take, RV with R less than 1, and as you let the R go to 1, you want that to have some kind of polynomial blow-up for some constant CMP. And one very nice thing about this is that the object on the left is obviously an algebra. You can multiply these two things, right? Because if you multiply in the interior of twistor space two things which are holomorphic, this polynomial growth condition will be satisfied. It's trivially to check. If you do f times g, the product will have polynomial growth condition. You will be changing, of course, the p, but it doesn't matter. And this tells you that you can actually, it is okay, it is legal to multiply holomorphic invariant distributions, something that it is a priori not entirely obvious at all. Why you should be legal to do that, if you don't have information about the wavefront set of these objects. Yeah. But this turns out to be possible always, kind of regardless of whether you have some dynamic condition on your metric G. It's just work for any G. And this is again great. So why is this great? And I will be finishing with that. This is great because this is the key thing that you need to solve tensor tomography for an anosov surface. So this problem of tensor tomography, we sort of first did it with Mikko and Gunther for two tensors, and then Colin and Guillermo a few years later realized essentially how to multiply these distributions as often as you wished. But in some sense, his approach was, it was in the anosov case, using somehow wavefront set information from the distributions that he was actually constructing. The nice thing about this theorem is that you don't really need this kind of anosov property. The algebra property was already there. We just didn't see it at the time with Mikko and Gunther, because maybe we were not thinking about the right sort of objects. But once you look at twistors space and you realize that this give you honest functions on twistor space, then you get very hopeful that you can actually take products of these things. And this is exactly what happened. And the kind of key result in the anosov case at the time that solved the tensor tomography for an anosov surface was the sort of analog of the Pesto-Bullman result. But now you don't have holomorphic functions on a closed Riemann surface. You only have constants. But you have holomorphic objects once you go to high order differentials. If you go to holomorphic one forms or quadratic differentials, cubic differentials, you have enough of these things. And this was the thing that we proved at the time, and we got a feeling that, these were kind of key, was that essentially, if you have an anosov surface, the map that, rather than taking the restriction to the zero section of twistor space, takes the first derivative, is actually surjective. It picks up holomorphic one forms, and you actually get all the holomorphic one forms by going this way. So in other words, if you give me a holomorphic one form, and you have B1 of them, where B1 is the Petit number, you can construct a nice holomorphic, fiberwise holomorphic first integral whose first Fourier mode is this holomorphic one. And once you have that, and once you know that you can take products, you see that this space of invariant distributions is infinite dimensional, because you start taking products of these things and you start sweeping out holomorphic differences of degree 2 and degree 3 and degree 4, and somehow with that, you can solve tensor tomography. That was the sort of basic idea that we had at the time. But now we have this sort of, twistor point of view for this. And just to sort of, if you don't know what an anosov surface is from a dynamical point of view, it's just enough, it's the C2 interior of the set of metrics without conjugate points. So if you have a metric without conjugate points and you perturb it a little bit, and it still has no conjugate points, that's the same thing of saying that the metric is anosov. So yeah, so this has been very satisfying. So the final message, this transport twistor set gives you a unified way to think about geometric inverse problems in 2D. In my own personal case, whenever I face a geometric inverse problem in 2D now, I'd always carry my pocket transport twistor, and I try to sort of look at the problem from the transport twistor point of view. That's kind of unavoidable now. We haven't used this set as a tool yet, yeah? So at the moment, it's just simply as a guide, because we are not really actually using the fact that it's a complex surface, but it's, it's a kind of nice, friendly companion that allows you to look at these questions in a unified way. And it's a generator of new questions that we haven't thought about before. So I leave you here with a couple of examples. So we think that if M is a simple surface, then the interior of this twistor space should be a spline surface. So there should be enough holomorphic functions there to separate points, and it should be holomorphically convex. And once you go to the anosov world, in principle, there's every reason to think that you're not going to be able to separate points, because you cannot separate points at the zero section, but there might be some holomorphic convexity that kind of survives once you go to the anosov picture. So it has generated kind of nice, sort of intriguing questions, and so I think this is probably a good way to stop. Thank you.
Thank you very much, Gabriel, for the very, very nice talk and for the very, very nice point of view. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself.
Hi, Gabriel. Could I ask one question? So for the boundaryless case, did you say that there are or there's no holomorphic line bundles without boundary?
Very good question. I mean, I didn't say anything about the case of no boundary for holomorphic line bundles. But one of the things that we proved in this paper is that just came out in the archive a couple of weeks ago, is that you have no non-trivial holomorphic line bundles in the interior. You have to be careful here once you go to the boundary. But
I see.
Yeah, we proved that in the interior, and we don't know what happens for higher rank holomorphic bundles in the closed case. And we do that just for the anosov case, because you need to have some kind of distributional analog of the holomorphic integrating factors, even for the line bundle case.
I see. Thank you.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Please feel free to unmute yourself. Okay, if not, thank you very much, Gabriel, for the very, very, very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you.